2, 1. Let's take it to the limit, shall we? All right. So now we're getting into it. We're getting into the fundamental calculus thing, the idea of limit. So in calculus, this collection of symbols was presented to you, and the justification you got for what this means is basically, well, the output gets close to L as the input gets close to A. Yeah. And that intuitive idea is kind of more or less right. I mean, that is essentially what is happening with it. But as we've hopefully picked up on, following mere intuition can land you into some hot water, because there are various things involving limiting processes that could go a little silly. So the goal is to make this precise, and in the process of making it precise, also not lose the intuition. And that is one of the problems when you do go to formalize mathematics. We don't want to lose, right? Right. We don't want to just delete everything we've learned before we got to this course. Although part of this course is kind of doing that. We do want to, right, recognize what we learned before is still right, and the intuition is correct, but there is a formal mechanism behind this that we didn't see the first time around. And we need these formal mechanisms because as we go further and investigate harder and harder problems, the subtleties, the minor points, play a much bigger role. All right. So that's our goal. We're going to make this precise, and in particular, there are a couple of things about this that we're going to make precise. So this is going to expand 2 videos. In this video, we're going to primarily focus on when this and this are finite real numbers. But then we will, of course, talk about when these things can be infinite, and we'll see that in the next video. All right, but for now, just bog standard, plain old limit. How does it work? How do we make it precise? Okay. So the correct place to begin is this part, as x gets close to a. Okay, so we got to make that precise. So we've got a point A, okay, and as x gets close. Well, what is x? X's are inputs for my function. So in calculus, normally with the functions, our domains are just all of the real numbers, or, if we get spicy with like a log or something, they're a nice interval. But as we've already kind of discussed, your domain doesn't need to be anything reasonable. Your domain can be just any subset of the reals. So limits then can be defined for any subset, but there's got to be something special about A, right? Because remember, as x gets close to a, the assumption here is that x doesn't actually get to a. It can get as arbitrarily close to a as you want, but it doesn't necessarily get to a, which allows us to talk about limits of functions that aren't necessarily defined at a. So, starting with the domain here of the function, certainly we can talk about anything, any function defined on any subset, but the a is going to have to be special. The a is going to have to be close enough to the domain, and that leads us to the following idea. Given a subset, we say that a point A is a cluster point of S if given a positive number delta. Then the interval, so we take A, subtract a little bit off, take A, add a little bit further. This interval and S without A, this is a non-empty set. So note the key point here: A does not necessarily belong to S. Belong to S there. Let's fix that. I have it in red too. I did not notice that. Because in my head it was right. Yeah, but anyway. All right. Yeah. So note A is not necessarily a member of S. You can be a cluster point of a set, but you don't belong to it. What does need to be true? There needs to be elements of S that are close to A. So given any delta, 1/10th, 1,000th, 1/100000th, so on and so forth, there are things in S that are that close to A, and the things are not necessarily equal to A. So in other words, cluster points are precisely the things that we can take limits of. So when I say limit as x goes to A, the A must be a cluster point, right? Because I want elements of my set to be arbitrarily close and not necessarily equal to it, which does give it kind of a clunky definition, right? I don't look at this and think this is anything particularly amazing, but it is capturing all of the ideas that I want, right? The arbitrary closeness, the belonging to S, and the not necessarily equaling A. It's all there in nice, precise set theoretic notation, right? It's capturing all of the ideas, right? Here's the formal mechanism that keeps that intuition alive, but right, we look at this and hopefully we go, maybe there's a better way to work with this. And in fact, there is. So our first goal here is to get two different characterizations of cluster points, both of which are a hell of a lot more useful than its normal definition. Okay. So before we go further, a couple of things to unpack about that last statement. These are called. Our book calls these cluster points, so I'm going to stick with that. And I will also say this is absolutely not a standard name for this. So depending where you look and where you're working with, people are going to call these limit points, not cluster points, because they're the limits of sequences. You will also see the name accumulation point, which is trying to grasp the idea of things are accumulating near it, hence the name. Accumulation point is, in some sense, technically better. And you might be going, well, why didn't we start with, like, this is our definition, maybe? That seems like to also capture exactly what I'm describing. It is, right, these are points that live in S that are that have these are points so that there are things in S that are arbitrarily close, and they're not equal to A. But note, this definition of it is very real number specific. This is very, right, it involves the inequality, it involves inequalities, it involves the algebra and an absolute value. It involves a lot of real number structures here, which is why, of course, we're going to prove this. But as I noted, this is a set theoretic creation, although technically it does involve algebra and intervals here. There actually is a way to get this to be purely set theoretic, if we were going to take some time to talk about the notion of open set, which we're not going to do. But if you're interested in that, then you should look up a branch of math called topology, which is a good time. One of my absolute favorite subjects. One that, even though I claim I'm an analyst, I've actually written 2 papers about topology, so it is a subject that I am very fond of. So this definition that's presented to us in Level's book, this is actually more in line with how you would define it for a topology, where topologies are, depending on who you're talking to, you're going to get very different ideas of what they're supposed to be. But, yeah. Anyway, so if you're interested, check it out. But anyway, so this is kind of the set theoretic way of handling this idea. And here's the real number way, and then from there we'll pick up the limit definition. And as you will see, points 1 and 2 here are the ones that are a lot more useful, and the ones that we will certainly use more. But it's good to have this to fall back on. There'll be a couple points where this will be nice. Alright, so let's go ahead and do these proofs. Alright, so suppose that we're a cluster point. Let delta be positive. Okay, then I know that this set is not empty. Alright, so that means I can find something that lives in there, and if something lives in there, alright, it's in this interval, and it's in this set. Okay. Hey, just like that. In that interval and in that set. If you're in the interval, that means this has to hold. If we're in this set, that means we're in S, and we're also not equal to A. Okay, so in particular, the former here is going to guarantee this is true, and then in my properties absolute value, we know that holds. And if this was actually equal to 0, then A and X would be equal, but that would mean A belongs to a set it doesn't belong to, which is contradictory. And that concludes it, and there we go. So if you are a cluster point, then you can find a point X, so that the absolute value of X minus A is strictly positive and within delta. So again, intuitively, cluster points are things that are arbitrarily close to our set. We can find elements in the set not equal to it that are as close to it as you'd ever want. And there we go. Yeah. Alright, so it's an if and only if. We prove the forward direction. Let's prove the reverse. So conversely, suppose that for any delta, there is an x, so that things make me happy. Alright, so I want to prove now that a specific set is not empty, so let delta be given. By assumption, we get this. Okay, clearly x cannot be equal to a, otherwise that's equal to 0. We're in S, and we're not equal to a, so we're in that set. Right, and finally, since the absolute value behaves, we know that x minus a then is between negative delta, and so x must live in that interval, which means that we're belonging to the set, which means that we are a cluster point. And there we go. Not bad. Right, so honestly, so far, this has not been a difficult proof at all. This really is just a true unraveling of definitions. It's worthwhile to do, right? Converting from set theoretic to more real number theoretic conditions, right? Having equivalences for a statement is always a good thing, right? You'll never know when you need a certain version of a definition. So, good stuff. But, right, not a particularly shocking proof. And actually, for the most part, all the proofs we will see with limits are mostly just sort of, yeah, it works. What you think should work works. That's a good thing. All right, cool. All right, now let's get to point 2, which says that if you are a cluster point, there is a sequence converging, and vice versa. All right. Well, by point 1, for any natural number, I can find an x sub n who is absolute value of my xn minus a is strictly positive and less than 1 over n. Okay, that guarantees that x sub n is never equal to a, so my sequence must live in the set S set minus a. All right, and now given an epsilon, I can find a capital N, so that 1 over capital N is less than epsilon. So for any n bigger than that, we get this, and thus that sequence converges to A. Oop, and there we go. Forward direction proven. If you are a cluster point, I can create a sequence living in this set that converges to A. Okay, right, and no. Right, given a delta, we found 1 over n's to make life work. There you go. Not bad. Okay. And, alright, now vice versa, suppose that we have a sequence living in that set that converges to A. So given any delta, there is a capital N, such that x sub n minus A is less than delta. That's good for all n greater than n. Since n sub capital X sub capital N lives in that set, we know that it's not equal to A, and thus that absolute value is strictly positive. And since it does live in S and has this as a condition, then point 1 guarantees that it's a cluster point. Ta-da! There we go. So, like I said, it's right. All of this is very just unraveling of definitions. Right, so far the only point in the proofs here that really involved any extra lifting was right here with the Archimedean property sneaking in, guaranteeing that the sequence that I created does in fact converge. But, yeah. Otherwise, nice and easy. Pretty, excuse me. Making all sorts of sounds here. Pretty straightforward stuff. Alright. Okay, well now that we've got a firm grasp of cluster points and how they work, we can now get to the star of the show. Let's actually define the concept of limit. Alright, so given a set S, a cluster point of S, and a function defined on S, then we say that L is a, note, a limit of f, and I want a limit of f of x there, actually, it's a bit better. Limit of f of x as x goes to a, if given an epsilon, there exists a delta, so that the outputs get as close as I want for any input that's close to a. So f of x gets close to L as x gets close to a. Precisely capturing the intuition, but now, of course, more formally, using epsilons and absolute values, which with sequences and limits of sequences, we saw was sort of the right idea to capture. This gets arbitrarily close. And again, note, this is formal, this is precise. Given a real number, you can find a positive number delta so that this stuff works. At the epsilon delta definition of limits. Oh boy. And like I promised, I think a couple of weeks ago when we were talking about Bolzano-Weierstrass, So epsilon delta is the bane of like everyone's existence when you first run into it. It's very infamous in terms of being like the worst thing ever. It's really not that bad. We will do an explicit example in a moment. But if you want somebody's name to curse for all eternity for subjecting you to this, the person to do that to is Weierstrass and Balzano. Balzano had it kind of figured out, but not quite. Weierstrass is the one who gave us this exact formulation of the epsilon delta definition of a limit. And as I mentioned, Cauchy was sort of doing this stuff, and if we're also going to be honest, Archimedes was also essentially doing this too. So going way back, so this idea it has been around for a while, but it wasn't precisely formulated like this until the late 1800s. Beautiful. All right, so there you go. Now, what are we going to do? Well, we have a thing, so we're going to do some proofs. And what's the first thing we're going to prove? Well, very similar to sequences, and as I stressed, nothing about this definition immediately says that L is unique. So, let's prove that it has to be unique. So, if we have a subset, a cluster point, and a function, and we have two candidates for the limit of f of x, did it again, as x goes to a, then L and M actually have to be the same. So if a limit exists, it is unique. All right. Now, this is a wonderful theorem to prove because, again, like when we did it for sequences, as I said, this is a very thematic proof. It's not a particularly difficult one, but a lot of the techniques that are on display are very common to a lot of the work, a lot of proofs that we'll see in the course. Just sort of the basic, a 2 epsilon trick, and right, really being careful about how definitions are set up, and blah blah blah. And this one is also really nice because something you may be noticing, you may not be noticing it, but your brain is. I can give you this, but there's no reason for A to be a cluster point, right? Right. What in here really needs A to be a cluster point? I could state this without this fact. But as we're going to see in the proof here, A needs to be a cluster point in order for you to actually do anything with this definition. So let's see that in action. Okay, so given an epsilon, what do we know? We can find two numbers. As mentioned before, what some people will do is like delta 1 and delta 2. I like to use different symbols, so I'll use delta and eta here. You free to use whatever you want, but there is a delta so that when the x is within delta of A, then f of x is within epsilon of 2 of L, and similarly when x is within eta of A, then f of x minus m is less than epsilon over 2. So we do the typical thing. We take the minimum of these two. So note, minimum in this case, as opposed to maximum when we did sequences. We want minimum because, note the direction of the inequalities here. Right, we want to activate both of these, so I need to be less than both of these in order for that to happen, rather than being bigger than both of them, which is what happened with sequences. All right, so we'll let nu be the minimum of the two. Note, nu must be strictly positive, because it's one of these numbers, and both those numbers are strictly positive. Excuse me. All right, so now what are we going to do? Now we actually use the fact that we have a cluster point. Because A is a cluster point of S, there is an element of S, so that S gets within nu of A and is strictly positive. So, whenever you've got a theorem, make sure every single hypothesis is being used. Every single one is being used. And there it is. So, we have used everything. L is a limit, M is a limit, F is a function, S is a set, A is a cluster point. And now, let's bring it home. Because S minus A is less than nu, that means it's less than delta and eta, which means that S satisfies this condition to guarantee that L minus F of S is less than epsilon over 2. S satisfies this condition, which guarantees that F of X minus M satisfies that, and there we go. L minus M is absolute value, is strictly less than epsilon for all positive epsilon, So it's got to be that L is equal to M. And the proof is over. That's it. Simple as that. Beautiful. Wonderful proof. So, again, as I mentioned with sequences, I love this proof. And I think I love it even more with the limits of functions. Because, again, it really emphasizes how we had to take the time to set up what a cluster point is. It is a necessary piece of the ingredient in order for limits to behave the way we expected them to. Beautiful. So beautiful. All right. There we go. So now equipped with this, we can say the following. If we've got a set, a cluster point, and a function that has a limit, that limit must be unique. So we'll call it the limit, and we give it the very familiar symbol, limit as x goes to a of f of x. So talk is cheap. Let's actually prove something from calculus. The limit as x goes to 2 of x squared is 4. There we go. All right. So note how I set it up, though. Given any subset that has 2 as a cluster point, let f be the function that just squares whatever you give me from s. So, note, this says that you could write this and it's always true. Right? Because the only way you could take a limit is if you have a 2 as a cluster point. And the function I want is just x squared. And this reveals that it does not matter what the domain of s is. This limit will always work. So you can write this, and that's totally fine. Right? You can write this without a reference to what is the domain of x need to be here. Right? Well, in order to be able to take a limit, you just need 2 to be a cluster point. And here we see it doesn't matter what the domain is. What matters is 2 is a cluster point, and the function I'm doing is squaring. So when we write all of those limits in calculus, where we really just don't give a shit about the domain, this reveals that, yeah, you really don't need to. The domain does not matter. What matters is that 2 is a cluster point of whatever the domain is. All right, beautiful. So, with that said, let's actually prove it. So, given an epsilon, what do I need to do? So the way the proof is set up, given an epsilon, I need to find you a delta. So, when I start my epsilon, I need to find a delta so that when x is within delta of 2, x squared is within epsilon of 4. Obviously, this is the delta I want. It's very clear. Right? You get it. Right, you see this immediately, and you're like, oh yeah, I get it. Yeah, I see. Right. Obviously, I'm jerking your chain there. There is no reason on earth that you should see this and immediately go, oh yeah, I bet that works. I mean, you should have a little faith in me that I did the proof and it works, but right. But at first glance, you're just gonna go, all right, sure, I bet it works. And this is probably right here is one of the reasons that the epsilon delta definition is so infamous, because the intuition of the limit as x goes to 2 of x squared, and you just go, well, yeah, it goes to 4. 2 squared is 4. Obviously where it goes to. Right? But the actual formal proof here, as we're about to see, right, this shows up for some reason. And right, there's no immediate reason why this is clear until you actually work out the details of the proof. And it's like, oh, that's obviously what delta needs to be. Given epsilon, that's the delta I'm looking for. Right, so I'm going to prove that if x minus 2 is less than this, then the absolute value of x squared minus 4 is less than epsilon. So, this is why, like I said, why it gets infamous, is because this, and it only gets worse. With x squared, it's kind of simple. With more complicated expressions, the deltas get much more, not easy to figure out. So it does feel like, nuking a mosquito or something, or killing, or my analysis professor, Professor Dempsey, always referred to things like this as using a bazooka on an ant. But it's necessary. We need these formal definitions. But again, right, the intuition is that it's 4. Now we'll formally prove it. Okay. So the first thing to note is that delta definitely is positive. 4 is strictly less than 4 plus epsilon. So we know that that has to hold. So there we go. Delta is indeed positive. At first glance, it might be a little clear, maybe why this would end up working. Kind of go like, oh, we got an epsilon, and 2 squared, 2, sure. So, no, delta here does depend on epsilon. It also looks like it depends on 2. That's interesting. Wonder if we'll talk about that next week. Excuse me. Alright. Now what? Alright, now before we go forward, I'm going to do a bunch of random shit, and there's a reason for this. So note, if I add the 2 over, square both sides, square this all out, oh, conveniently the 4's cancel, and oh, look! I have an explicit formula for epsilon in terms of delta. I wonder if what I did was look at x squared minus 4, made that less than epsilon, and then figured out how to get epsilon in terms of delta, and then create the delta so that this holds. Yeah, that's kind of what I did. Alright, so now, let's let x be within delta of 2, strictly positive. Now, excuse me, I'm now going to look at x plus 2's absolute value. Trial inequality guarantees that this holds. Now, why would I do this? What's x plus 2 times x minus 2? Oh, yeah. X squared minus 4. F of x minus 4. And now, hey, this product here is delta squared plus 4 delta. So, this is exactly how I actually did the proof. I started with this, I factored this out, I then went, if this is less than delta, x plus 2 has to be less than delta plus 4. So, whatever my delta is, I need delta squared plus 4 delta to equal epsilon. Oh my god. Oh man, I got some dry throat down here. Yeah, sorry. Ugh. So yeah, so then I got delta squared plus 4 delta is equal to epsilon, and so that told me what I needed to do is solve for delta. Right? In fact, that's just literally quadratic equation, and then you solve for it. No joke, no cap on that. Yeah, there you go. So that's how I actually did it. I started here, got here, figured out that if this was less than delta, this was less than delta plus 4, then I got delta squared plus 4, so I set that equal to epsilon, and then I solved for delta, which gives me this. It's plus or minus, but I obviously want the, non-negative one. And then equipped with that, right, then I just set delta equal this, and then formally work out the details. And there we go. Alright, well, if you thought that was a great time, then you're going to love the homework. Alright, cool. Okay, so, one last thing for today, which is the following. So, we will now prove that there is a way to compute limits using sequences. And it turns out that this ends up being a very powerful theoretic tool. It's not the best computationally, so when it comes to computing limits of things, this can end up being very misleading, because it's possible that you're always picking sequences that work, but there's some sequence that doesn't. But this ends up being a theoretically powerful tool, so let's check it out. Alright, so if L is the limit of f of x as x approaches a, then that means any sequence... Oh my god. Sorry. Converging to a, when I feed it into the function, it converges to L. So if we are to be the limit, then that means sequences have to be working as well. So this gives us, like I said, kind of a nice theoretical way of dealing with limits. And in fact, what makes this really nice is the applications of this, because we already know a bunch of properties that limits of sequences have. Limits of sums behave, limits of products behave, limits of inequalities behave. So all of that work we did for sequences, we can just carry them over for limits. Alright. Alright, so this turns out to be a pretty easy proof. So suppose L is indeed the limit. Take a sequence converging to A. Give it an epsilon. We know that f of x minus L gets within epsilon for all x that are within delta. Now I have a delta, which is positive. The sequence converges, so that means there is some point in the sequence where the elements of the sequence get within delta. Note that all the elements in the sequence are not equal to A, so the absolute value has to be strictly positive. Okay, and then that means since they're within delta, their output is within epsilon, so the sequence then converges. Given an epsilon, I found a capital N, so that f of x n minus L gets within epsilon. Beautiful. There we go. And note the ordering the way this had to go. I had to start with my epsilon to get my delta. Given my delta, I now apply that to the sequence. So that's kind of the tricky part here, because your initial reaction might be to use the epsilon for the sequence, but that doesn't get us anywhere because the sequence is being plugged in. It's the inputs. So the delta is for the inputs. The epsilons are for the outputs. All right, so it's an if and only if. So we've proven the forward direction. Now we want to prove the reverse one. And what's cool about the reverse one here is we're actually going to do it contrapositively. You could do it directly, but it's actually really interesting. The direct way is actually a huge pain in the ass, and the contrapositive way that we're about to do is super easy. So it's a really weird. It's one of the few proofs that I know of where it's like it's just so much easier to just do contraposition. It's like the only one I know where like contraposition is like the better way to do it. So what does that mean? So instead of assuming this and proving this, I will assume the negation of the original and prove the negation of the second one. So that means we've got not Q implies not P implies not Q, which is equivalent to Q implies P. So suppose that L was not the limit. What does that mean? Okay. Well, if it was the limit, that means given any epsilon, there is a delta, so that for all inputs, things are working. So the negation is there is a bad epsilon, but for each n, I'll be able to find an x sub n in S so that I get arbitrarily close, but the outputs are bigger than epsilon. Right, so if we were the limit, that means given an epsilon, there is a delta, so that my statement is working the way I want it to. If we're not the limit, then there is an epsilon, so that for any positive number, I can find an element in the set that's not behaving. So since 1 over n is always positive, I can now simply create my sequence. But now, note, the sequence by its construction will converge to A, but the output sequence does not. Where's the does not? Okay, there it is. Does not converge. Right. For if the sequence did converge, then that means at some point f of x sub n must get within epsilon of L, but it's always strictly greater than epsilon. So by contraposition, if the limit does work for any sequence, then the limit has to actually equal f of x as x got a c. Why is there a c? It's not even close to a. These little goofy things here. All right. Okay, so let's unpack this again, because right, this is a bunch of logic hoops are being jumped through here. Right, so we're supposing L is not the limit because we're doing contraposition, starting with the negation of what I want to conclude with, and then I'm going to end with the negation of what I wanted to start with. Okay, so since we're not the limit, there is a bad epsilon, so that for any positive number, there are elements that are within that positive number, but the output is greater than epsilon, so the positive numbers I pick are 1 over n. Oh, God. That forms a sequence that converges to A, but the output does not converge to L. So, there we go. If we're not the limit, we can find a bad sequence. So if every sequence works, it's got to be that the limit is working. Right? Because if the limit doesn't work, we can find a bad sequence. Beautiful. All right. So, like I said, equipped with this, we can now establish multiple facts about limits and algebraic ideas. So specifically, if I have two functions and their limit exists, then the limit of their sum exists. And the way we prove this is, well, take a sequence converging to A. We know that the limits of a sum of two sequences is the sum of the limits, and therefore the limit of the sum of the two functions, its limit must be the sum of their limits. by the previous proposition. Beautiful. Right? Okay, and so following this format, applying the previous proposition to guarantee the existence of certain limits, you could then verify the following propositions. If f of x is less than g of x, then their limits behave. Similarly, if I have three functions, inequality like this, and the one on the left and the one on the right have equal limits, then the one on the middle gets squeezed the way you want it to. Limit of a product is the product of the limits. Limit of 1 over is 1 over the limit. So on and so forth. So pretty much anything we prove for sequences can be properly put together for limits. Okay, beautiful. Now, if you are asking, hey, can you talk about the lim sup of a function? The answer is yes, and we are not going to. Sorry. But it is a thing that you can do. It's a much bigger mess to define than you would think. But, yeah. So we will not be talking about that, unfortunately. But it is a thing if you're interested. All right, and there we go. That finishes our first taste of limits. So, like I said, our next video, we are now going to start asking what if this is infinity? What if the limit is equal to infinity? What if I'm coming in from the left? What if I'm coming in for the right? Ooh. All right, so that's the plan for the next video, and I'll see you there.